Hi, I'm Junhyung Lyle Kim. I'm a fourth-year CS PhD student. In this video, I'll talk about local stochastic factor gradient descent for distributed quantum state tomography. And this is joint work with my friend Taha Toghani, Professor Cesar Uribe in the EC department, and Professor Anastasios Kyrillidis in the CS department. Please note that I have another video titled Fast Quantum State Reconstruction via Accelerated Non-Convex Programming. This current work expands upon that work, so please refer to that video first for background information. So I'll directly jump into the objective function. Just like the previous work, we are going to include the low rank list as our prior, in which case you can ignore this unit trace constraint without affecting the final solution. And I already mentioned this RFP restricted isometric property on calligraphic A. And David Gross, in his previous paper, showed that one can reconstruct a rank R density matrix rho using R times D times polylog D measurements. And I remind you that without any prior information, without the low rank prior information, you need D squared number of measurements. So if R is much smaller than D, we can reduce a lot of sample complexity. And I remind you that Liu showed that the sensing matrix that's actually used in quantum computing does satisfy this RIP. So it makes sense to utilize this compression technique. However, because D grows exponentially with the number of qubits, even with this reduced sample complexity, it can be very large. So here I'm plugging in the rank equals 100 for 30 number of qubits. That still reaches this huge number. So how should we really handle this? Before moving to the distributed objective, we're gonna review the factor gradient descent. So just like the previous video, we have this convex constraint, convex PSD constraint, and non-convex constraint. So we propose to reparameterize rho as UU transpose, in which case we can rewrite this problem as an unconstrained problem. So now we live in the smaller search space, and the problem is unconstrained. And I showed this factor gradient descent from the previous slide, previous video. But from the previous slide, we saw that this M is still very large, even with the low rank constraint. One easy way to mitigate that is to use stochastic factor gradient descent. So I'm just simply replacing this M with B, and B should be much smaller than M. So we're gonna build a distributed algorithm based on this stochastic factor gradient descent. So as I mentioned, there's this explosion of data, even after applying this compression technique to reduce the sample complexity. So to handle that explosion of data, we consider the case where the measurements and the sensing matrices are locally stored across n different classical machines. And these classical machines can perform some local operations based on the data that they have and communicate back and forth with the central quantum server. So this was the modify centralized objective, where we applied this factorization to transform the constrained objective to an unconstrained one. But now we're going to use this distributed objective. So now we have m number of classical machines, and each machine has their own loss function gi. And that gi has this similar form. And pictorially, we can imagine this case. So we have the central quantum server, and we have number of local machines. Let's say this is the ith machine. Then the ith machine has calligraphic A of I sensing matrices and yi as the data, local data, which has mi components. So if we collect all the sensing matrices from all the local machines, and if we add up all the number of data that each machine has, then we basically recover the original case. One thing to remember is that this type of intra-node communication between server and local machine has shown to be much more expensive, typically about 3 orders of magnitude more expensive than local computations. So we want to communicate as little as possible. So that yields our algorithm called local stochastic factor gradient descent. So we have a number of predetermined communication steps. This first one is initialization. So the algorithm goes as follows. For each time step t, and for each machine in parallel, each machine is going to sample uniformly at random from the number of data that each machine has. Now, if the time step equals one of the predetermined communication steps, then we're going to collect all the estimates from the data, and we're going to take the average. If not, each local machine will just perform stochastic factor gradient descent without communicating to the central server. This is why we call this local stochastic factor gradient descent. Based on the algorithm, we have two theoretical results. So first one is that if you use a constant step size, then you can achieve something called linear convergence rate up to a neighborhood that depends on the step size and some noise term. So as a remark, so the last variance term is further reduced by this number of machines n. So if you have similar expression for centralized case, then you would not have this n. So this shows one advantage of using distributed method. And obtaining this result assumes single batch. So if you use batch size b greater than 1, then this term will be further divided by additional factor b. And by plugging in h equals 1, h is the maximum number of local iterations that each machine can perform without communicating. So h equals 1 means local stochastic factor gradient descent recovers stochastic factor gradient descent, in which case this first term disappears, and that essentially is the same local linear convergence rate of SFGD. And then by using a properly diminishing step size, in the next theorem, we show that you can essentially converge exactly at the expense of diminishing the convergence rate to a sublinear rate. So this rate is slower than the linear rate from the previous slide. I have some experimental results and more details at my poster section, so please consider coming to them. Thank you.